Yamaguchi. He's the chief scientist of Shift Left and the managing director as well. And he's going to be talking about elegant and scalable code querying with code property graphs. Thank you.
Yeah. All right. Yeah, first of all, I'd like to thank George for the invitation to come here today. I'm going to talk about an application, essentially, of well, what used to be built entirely around graph databases. Today, it still has a lot to do with graphs, and but we ended up more or less creating our own graph database around this. But overall, I think it is a topic that probably belongs here, but also brings in some things that might be a bit unusual. So overall, Shift Left is actually a company that deals with security. So what we try to do is we try to identify vulnerabilities and bugs in code automatically. This actually has a lot to do with the work that I did during my PhD, which was all about finding vulnerabilities using machine learning techniques on graphs. Eventually, it became clear that only unsupervised machine learning would make sense in a practical setting. So I actually then ended up calling the thesis pattern-based vulnerability discovery, and it was a lot more about how to find patterns in graphs and how to describe them actually with query languages. And that's kind of my connection to this community here. All right, so I'm going to talk about essentially two programs here. One is called Ocular and the other is Yarn. And what you can think of these as essentially extensible code analysis machines, we like to say. And so, yeah, like a virtual machine that understands a query language and that can be scripted with JVM-based languages, in particular in Scala. And you can use this to query for patterns in your code. So the goal might be to identify bugs and vulnerabilities, or to simply get an overview of a large code base. So let's say you have a program that you've never seen before, and at first you want to know, well, what are the different routes into this program? How can I interact with this program? How does it interact with APIs? What are the flows in the program? What are the kind of information flows here? These kinds of things. Yeah, that's all. Those are all things that we want to be able to express in queries. Yeah, we've written a lot of scripts and language extensions on top of this machine. Luckily, today there's also an open source version, so you guys can also try that out if you like. So Yarn is actually the free-spirited open source brother, you could say, of Ocular. This talk is not about the products specifically, but more about the underlying technology, about the graphs, essentially. All right. So what does program analysis have to do with graphs at all? Well, if you think about the different kind of representations you get inside compilers, or even if you're just programming and you want overviews of how the code is connected, then very often you end up with graphs. So what you see here is an abstract syntax tree. So that's what you get when you parse the code, and then the code is represented as a decomposition of its language constructs. Or here, this is what's called a control flow graph, where you can see how you can get from one statement to the next, or a dominator tree that will tell you if I want to get to this statement, is there any statement that I need to pass through? So that's all on the compiler level, but then there are also things like class hierarchies, for example, or just package structures, really. All of these are graphs, and all of them provide a different perspective on the code, which might be useful to ask particular questions about it, but only very limited questions. So the main idea was, what if we merge these representations? Can we then maybe describe a query language that allows us not only to ask all of these questions that we could with the different perspectives, but also to transition from one perspective to the next? Yeah, the property graph was actually a good fit here, because essentially what we want to do is we want to describe different kinds of relations within the same graph. So we need these edge labels. And then apart from that, of course, we need to somehow store data. So the key value pairs that we can store in the nodes, they can help us store that data. And so that initial idea is actually a bit older now already. So we published a paper actually at a security conference called Security and Privacy, and that introduced this very basic concept and only merged 3 representations from compiler construction. This didn't really say a lot about what that graph would look like. There was not even some sort of schema. It's just, you know, the very basic idea of merging these and then seeing whether we can formulate queries to describe common vulnerability types. And we did that with Gremlin, actually. Today we still use Gremlin, but you can hardly see it at this point. But it became clear we need some sort of specification, something that people can actually write against. And the main problem we had was the original code property graph would only work for C, C++, but now we wanted something that works across programming languages. Once you do that, you'll also realize you don't want to re-implement this for every language again and again, so you're kind of asking yourself, what is the minimal specification that I can give for language front-ends to implement, and what can I do later on language independently in terms of analysis. We have an open source specification today, which you can find on GitHub, and this essentially shows the main picture of the spec. So it's really, it didn't become that complicated in the end. We model types, we model calls, we model methods and files and namespaces. There's a bit more. We model lambdas as well. A lot of these things are then achieved with extensions that are implemented on a per language basis. So if a language does not have lambdas, then we don't even pull that in. But the main construct that we have here, the main idea of the representation is to say, let's create a container format for any programming language. And essentially a programming language, if you think of it, it's a set of operations. And you can see each operation as a function call. And so what you really need to model is function calls, and you need to supply semantics for these function calls, saying, so what happens, how does the data flow for this method, or whatever it is that you want to model. And that's essentially a specification that we have, and we've been using this for about, I'd say, 1.5 years now to implement these different language front ends. So today we have the ability to map Java bytecode to our first level code property graph. We can do this with C#. We can do this with LLVM bitcode. We can do this with Golang and a bunch of other languages, including dynamic languages such as Python and JavaScript. And so we have that first level CPG, and then in the second level CPG, we essentially do some sort of linking, which is we ensure that when we create the first level CPG, you can more or less stream out the graphs. It's a very local analysis that we get here. And then when you have different graphs for all of the methods and types, then you start connecting them in the back end, where you have more control over your memory. Because this thing here in the front, that usually runs on the customer side, and you really don't know what you'll get in terms of memory and performance characteristics. So this gives us the base layer of the code property graph, and you can think of it as a production quality version of what we already had in 2014. It's language independent, a language independent intermediate representation. You can do control flow analysis over it, data flow analysis, and we build a powerful data flow tracker on top of it, which is interprocedural, and a few other attributes that are relevant to get precise results. And it's pretty fast. All right. And so I just want to show you what you can do with this, because that's all very abstract. Let me give you some examples of concrete things that you can find with this base layer. So this is a vulnerability type that's been known for a very long time. In 1991 it was first presented, and it was then rediscovered in 2018 by a startup which gave it a fancy name called ZipSlip. And the idea of ZipSlip is that if you have a zip archive and the file name in there has a .. in it, then you can actually break out of the directory structure and you can start overwriting arbitrary files as you extract So that's an obvious security vulnerability because you might then be able to overwrite some file that belongs to the user, maybe some file that's a script that's executed next time the user logs in, and boom, you execute whatever code you like. Now, what would that look like in Java? I mean, it can look very complex, but this is like the most simple form. So you have a zip entry, and you say get name on it, and then you call a file constructor. So that means you're opening that file, and if there's no sort of validation of this entry get name, then this could contain that .. and then you should check the code to see whether there's a vulnerability there or not. And it's totally sufficient here to model these things that I just said, control flow, data flow, method invocations. If you have that, then you can model that, and this is what a query would look like for that. So we define sources, we say, look at all the methods where the full name matches Java util zip get name, and go to the method return values. So look at all the return values of get name. And then as a sink, look at all of the methods that are called file init, so that's the constructor. From there, go to the first parameter, and then give us all the sinks that are reachable by the sources, output the flows, and also check that it does not pass by an escape, sanitize, or contains. There's actually gremlin underneath, so gremlin Scala, but yeah, might not even be so recognizable anymore, I'd say. Oh yeah, and we used this, we found a bunch of previously unknown vulnerabilities, reported them, so this works. I'll give you one more example. This is called an XXE vulnerability, XML external entity processing vulnerability. And the idea here is that if an attacker controls an XML document that is processed by your application, and then there's this particular setting that has not been made, which is disabling of external entities, then what the attacker can actually do is they can load external entities, and via a few steps, this also leads again to a code execution situation. Now we would need to check, is XML parsing happening, and is nobody calling these set property methods that would make that safe? And that's what the query would look like. So again, we create a data flow query that says, go to consider all the XML stream reader next calls as sinks, actually the instance parameter of that, and then as sources, consider XML input factory create, then do a reachable by query to see if that actually, if there's a data flow there, and make sure that it is not the case that somebody calls set property on one of those XML functions, and that there's a call to that. And that's it. And we also used that and found a bunch of XXE vulnerabilities, also reported those. So this is quite powerful, but it's not powerful enough. So the problem really is, and this is something that really just became clear at Shift Left, I guess. The problem is that users actually want to reason about vulnerabilities on a much higher level of abstraction. You want to talk about, let's say you have a web application, you want to talk about forms, you want to talk about routes, right? You want to talk about requests, HTML attributes, input fields, JSON responses, information flows, databases, files, handlers, these kinds of things. All of that does not exist on the level that typical compiler optimization passes work on. That's not in the control flow graph. So what we would need is, we would need to take that base layer, and we have a query language defined on that. Now we want to extract some information, and doing that, we create a new layer of the graph, which contains higher level abstractions. And for those higher level abstractions, we again want to be able to define a query language so that we can talk about these new abstractions as well. And yeah, that's what we implemented. And I'm just going to give you an example of one of those higher level abstractions. One thing you need in web applications is handlers and routes. So this is the Vertex framework, a typical example there, where someone says, for the route greeting, I want to specify that this is the handler. So you have a Lambda function here that will be called when somebody browses to greeting. So you kind of, you have the control flow graph, you have the data flow, you kind of need to start querying this to then create a route and a handler and link them together. And that actually this code does that, right? So we're not going to go through the details here. My point is, you see this reachable by here again. It's that level of abstraction where we talk about data flows and control flows, but since we have that nice API to ask questions about that, code becomes very short to create a new level that contains other abstractions, and then you can work with those abstractions, and so you get this nice little, multi-level graph representations that goes higher and higher in terms of abstractions. Here's a similar example, also just to show you that it fits on a slide. This is a pass that we wrote which will essentially create a JSP DOM tree so that you can start talking about forms and input fields and these kinds of things, which are also not part of your standard compiler representation. And then we can say things like CPG form and make sure that it's a method post and go to all the input fields. And let's say we want to make sure there's no attribute called HTML escaped to filter for things that are actually not cross-site scripting vulnerabilities, another vulnerability type. And then again, we can work with this reachable by. But you see, we can transition from one abstraction to the other within the same query language. All right. And then there's actually a lot of information, what people typically call business logic, that's actually not really in the code. And you also need to incorporate that. Because a lot of people will complain when you talk to them about static analyzers, about programs that try to find bugs in other programs. They will complain about false positives. When you look into the academic literature, you'll see all sorts of reasons for false positives that have something to do with the core analysis, over-tainting of collections, conservative core graphs, and all these kinds of things. But in practice, it turns out this is actually not the major cause of false positives. The major cause is things that you simply cannot see in the code. For example, this is an internal service that only our admin uses. Or without first convincing the authentication server, this code would never be executed. Or due to aliens, this integer is always 5 and thus cannot be negative. And so you need a nice way of taking this business logic and getting that into the graph as well. And we also do this with these CPG passes, where essentially we take that information and we tag it into the graph, and then we can make use of these tags as part of our queries. And so this is what code property graphs look today. Multi-layered structure. You begin with that base layer. Then you have a few layers on top of that where you link methods and types. And then you start off with domain-specific layers, like web application-specific layers, system code-specific layers, maybe something that brings in some business logic. And on top, eventually, you have the vulnerabilities, the findings that just say that allow someone to just say, OK, so what did you find? And now bring me all the way down to the code that you think is connected to that and all the different attributes that led to this discovery. Now, so yeah, one more thing that's really nice about this whole design is that it actually scales pretty well. And we have Scalable in the title, and so I just want to quickly talk about why. So scaling static analysis generally means calculating summaries where you can, kind of like dynamic programming. You always want to make sure that you never calculate anything twice. Now, if you look at these layers, creating summaries about data flows, saying, well, I've seen this flow before, you don't have to analyze this again, that's pretty normal. But we can actually, we summarize all sorts of things with these layers. And so we can always, when we look into the second or third layer, we actually have cached information about what we've calculated before. Now, the second thing that's nice about this whole CPG pass API is parallelism. So processes aren't really getting much faster, we know that, but you can calculate lots of things in parallel today. And the CPG passes are kind of parallel by design. So the way this works is you have your base layer, and then you can execute all of these passes in parallel. Each of them creates an overlay, and then there's kind of like a reduction step, and that's when you get these CPGs with overlays. So we do a lot of parallel computation here to make things scale better as well. Yeah, and with that, I'm done, and I'm happy to take questions. So for Java, we do this on bytecode. For C#, we integrated this with the Roslyn compiler. The thing is, when you integrate with the compiler, you need to make sure that this is everybody uses that compiler. For C#, you can kind of do that. For C, for example, you can't do that. And for C, we chose another route, fuzzy parsing. So we've tried all the different routes, and yeah. Currently, it does it for C#. We're working on more, but yeah. Right, yeah. No, we currently analyze Python via an AST that we get from a Python library. Again, you can choose multiple routes there, and yeah, it's always the design discussion of which route to take to cover most needs. That's always yeah, difficult one. Mm-hmm. How data is sort of derived, especially here goes as part of the SQL script. Is that something that is like SQL injection or? No, just script, like the code that you have. Code paths and procedures. Yes. Yeah. So you have a lot of code, like SQL code. Ah, I see what you mean. Variables, you do something to it, yeah. Compute or derive data out of it. Yes, so yeah. You're able to trace that, ensure traceability of what was the input and how was the output. Yes, well, I guess, I mean, this was all static. I guess if you want to do this kind of tracing, you would want to additionally take some information from actually running the program and integrate that into the graph. Exactly. Yes. Even to actually get a first pass understanding of what is it actually doing. Yes. Because this is important for legacy code. Yes, yes. Yeah, exactly. Yeah, that's kind of the point I was making when I said it's about understanding code as well, not just pinpointing vulnerabilities. Just how does this thing, how is it even exposed to the world, and where does the input come in? Yeah.
Kind of following up on that. So you're parsing code and basically coming up with the graph. Mm-hmm. Have you considered actually using graph algorithms to do analysis of the code? I can see obviously you're taking that and then using graph queries to look at it. Yeah. But have you thought of looking at actually graph algorithms to understand what are key functions, etc., from that point of view of understanding your code base? Right. What are the really significant parts of this code that we need to look at that if this breaks, how can this impact everything else?
Yes, yeah, we have thought of that. We have tried around some things. Essentially, we've written a lot of different scripts to explore, what can you do to find out the overall structure of the code. And then there are going to be like hotspots that you want to identify. What's actually also interesting is if you start getting in the revision history, because then you can see which is actually the code that's been like this for a very long time, and where's code that changes a lot, and should therefore be analyzed again, something like that. Yeah. Does it answer your question? Yeah.
Do you have to write specific bitcode code for every single program you write, or do you have a library of all of the vulnerabilities that you know and you literally run once and check?
We have a library of the vulnerability patterns for the most common frameworks, because that's how you need to think about it. Like if somebody brings a Spring-based web application, what do you look for? And then you take out that library and you run that automatically when you detect Spring, and then you have that product again that many people want, which is just something that spits out security findings. But the real power here is that you can tune this, right? You can actually look at this and say, oh, well, these things don't make sense to me. I'm just going to tune this a bit, and then false positives are gone, essentially, or reduced, I should say. All right.
Great, thank you so much.
Thank you.